please go ahead.
Okay. Thanks, Miguel, for this nice introduction. Before starting, I'd like to say thank you for this invitation to give this seminar here. It's actually my first time here with you guys. It's a pity that it's going to be like this virtual and not in person, which I hope it can be done soon. Now the vaccination is in a way getting faster. So yeah, you're right. I'm going to talk about this new news about the G-2. And this is going to be that's how I thought. As it is in my mind. That's going to be an informal discussion. What does it mean? That this is not going to be a regular seminar. I'm going to explain you a fairy tale about this new guy in town, and I'd like to ask you that in any moment you just jump in whenever you have questions, comments, I don't know, queries, criticism, whatever. Okay, that's the idea. So I'm going to present the things, present the characters there, and if you have something to say, just say it. Okay. Um, that goes for you at home or in your office, but also in the seminar room, so I can hear you well. So please do that. Okay. It is going to be like that. I even didn't write any conclusions. So I really like to share this thing with you and see how it evolves, no? And how can that thing I'm going to present can be connected to other flavor anomalies for you. Knowing that you guys are experts on that as well. No? So let's see how it works, okay? Let's see. I hope you have heard about this G-2 because even in the regular press media, yes, realize that. No? There was a comment here. No.
No.
Oh, okay, sorry. So I just got some few of the journals discussing about this thing. For example, El Mundo, El Periódico El País, or even this Ara from Catalonia, where they were discussing about this new guy that seems to appear just recently, right? I'm just mentioning that because it's quite difficult that some physics appear in the so many newspapers at the same time. And I like to say, call your attention on the titles they use. So for example, this one, I like it the most from the El Mundo, no? El Muon, the particle, the rebel particle. And they were using this image from Einstein with the R here written in this blackboard. No? Okay, so they really got a lot of attention, I guess also because they are a bit tired of just news about COVID. But this is also interesting because actually this G-2 is a quite a simple physical situation, physical object, and it's related actually to this is the outline of the talk about a spinning tops. No? But that's just a cartoon. That's the real outline I'm going to discuss today with you. And this is going to be in this form of news, no news from two different sides. I'm going to discuss about the news from the last experiment, Fermilab. I'm not an experimentalist, so sorry for any inconsistency there, but I'm really looking forward to discuss with you this thing. And I'm also going to discuss about the news from the standard model calculation. I'm going to be a bit critical on that. I'm going to scrutinize the standard model and discuss with you the strong and the weak points, okay? I'm not an expert on new physics, so I just put here in the outline new physics in quotation marks because I'm just going to give you a really, really brief point of view, my point of view here, but open to discussion, okay? So why to talk about the G-2? Not only because of the news in the press and the recent results, but also in words of Arkady Weinstein, because one is interested in the G-2 because it's the whole particle physics in a nutshell. And that sentence appeared in his book where he discussed all these objects in full detail. Why is so? Why is particle physics in a nutshell, and why is at least I'm interested in? It's because this G-2 is measured with that precision that whatever thing you know about particle physics must be put there in order to calculate the object that our experimental colleagues are measuring. Everything you know about particle physics would enter, not only say electrodynamics, but all the renormalization theory, all the standard model, all these techniques would appear there. Okay, but okay, let me be a bit more concrete. What we are talking about? Well, it turns out that as soon as you have a particle that has electrical charge, it has a spin, or spin 1/2, for example, and you put it in a magnetic field, you will say that the energy of the system would get an extra contribution, a new contribution coming from the interaction within the spin with the magnetic field. And the proportionality here is going to be called that's the standard magnetic moment, and it's going to be proportional to a factor called G, that is the so-called Landé factor or gyromagnetic ratio, G, okay? This factor G is something that within the theory can be easily calculated if you are considering a purely relativistic, non-quantum mechanical framework. For example, the Dirac theory, you would get G exactly 2, okay? But it turns out that the quantum theory, which includes radiative correction to that, would tell you that actually G is not exactly 2, because the G factor is in a way measuring the structure of this elementary particle. Structure in the sense that all the inner properties would show up, not only spin, which in this case requires G equal to 2, but also the fact that we know that the particles traveling would have a sort of a cloud of other particles around. And the properties of that particle would know about the clouding of that, okay? For example, the first deviation from the Dirac value, G equal to, the first deviation, the first departure, is going to be of the order, as you can see here downstairs, of 10 to the minus 3. That's a small departure, right? And it comes from this loop where you have the Muon line, that's a solid line. In blue, you would have your external magnetic field, and it may happen that being this Muon relativistic would emit a photon, and then it would catch it later on. So this loop thing would provide a contribution to this factor G. And we are going to look at to a parameter called A, that's just a number, that is really the deviation with respect of 2. You see, no, that G would be equal to, A would be equal to 0, and we call A the anomalous magnetic moment. Why anomalous? It's not because it's an anomaly in the quantum field theory sense, but it's more that it's a departure from the Dirac theory. So it's an anomalous thing with respect to the Dirac theory, okay? But it's well understood within the quantum field theory, okay? Let me put you in context. Is this a new thing? Oh, actually, when you go back to the history of particle physics, it turns out that the same object, this G, was crucial to abandon the classical physics and to say marry with the modern techniques, modern theories. In particular, for example, when Dirac proposed the relativistic theory, he proposed actually that G would be, or predict G would be 2. And it was the measurement confirming G equal to that allowed them or triggered them the need to abandon the classical theory, okay? And the same object later on, we are talking now, say, at the end of the 40s, last century, the same object, but measured with more precision at the level of per mil level, at the per mil level, the experiment observing a deviation with respect to 2 plus a theory understanding the effect plus the lamp shift experiments that went all together with the corresponding theory was then the starting point of the quantum electrodynamics. So the same object that helped Dirac to confirm his theory then was useful and necessary to abandon the relativistic theory to marry the quantum electrodynamics, giving then later on the idea of the gauge theories and the standard model. So the situation we have now, you see, no, historically that's a very interesting object, and the situation right now is that we may now be seeing a deviation, a similar deviation, say pointing towards a new paradigm, saying maybe that the standard model, the QED, maybe is not the right theory. Okay, but you see the role of this object all along the last, say, 100 years. No? And what is the situation? Okay, let me put it before the Fermilab result and then later on. Okay, I like to do that because things have been changing a lot, but not that fast as one can think. What was the situation? So you may already know that the Fermilab the Fermilab G-2 collaboration released a new number for this object, a new measurement, and that was 1 month ago. But before, we already had a result that was super precise, and that's the central value here in this slide. That was a measurement performed at Brookhaven with a Muon storage ring. I'm going to comment later on that, and with a precision requiring 10 to the minus 10. So it's with an error 610 to the minus 10. So super precise. And at that time, that's a result coming from several studies around the early 2000, and finally published in 2006. So it's all 15 years old, a bit more. And it had a counterpart, a theoretical counterpart. But the problem at that moment is there were several theoretical results in the market, and then you would pick up your preference, your preferred theoretician to give you the number, and then you would compare. That's why when you look at the standard model versus the experimental result, and this is this delta A mu, you would get a discrepancy that may reach from 3 to 4 sigma. That would depend on what standard model result you would take. No? And I'm using, for example, here, the one from Jäger-Lerner-Niffeler 2009 review, that would compete in precision using the 610 to the minus 10 as well. So that would compete with the 610 to the minus 10 from the experimental result, and the discrepancy would be around 30 in these units, 30, 10 to the minus 10. That would go around 4 sigma. No? So the discrepancy was really large. So you are seeing a deviation at that time. So both theory and experimental communities decided to go for understanding better those errors, trying to reduce them, trying to scrutinize them carefully, and ultimate goal, try to see whether this discrepancy would vanish or would go to 5 sigma. Okay. And those are going to be the news I'm going to discuss with you. One is the experimental one, and the other one is the theoretical one. The theoretical one came first, and that was basically under the name of a theoretical white paper coming from a theory initiative that gathered more than 100 people discussing, working on that topic. And they gathered all together. They put finally they decided to they got a consensus for what would be a standard model prediction. Okay, and then they released this number here downstairs with a precision 4 10 to the minus 10. So this is actually a reduction of the error, okay, but not reaching the goal you would have in order to reach 5 sigma. But okay, that's going on the way. Also, the Fermilab experiment is thought to reach at the final life of the experiment a factor 4 compared to Brookhaven in precision. So, and that's actually what they released 1 month ago. Those are the numbers, and this is in particular the Fermilab one. Yeah, sorry, yeah, that's the Fermilab one. So they didn't get this precision 1.6 into the minus 10, but they are going towards that number. And this is the image, the sketch of what's the current situation, where you can see here in blue the Brookhaven result, which is this one here upstairs, that has 2 different sources of errors: statistical the first, systematic the second. When you combine, you got these 6 I was mentioning before, but you can already see here that the error is dominated by statistics, which is actually the same that happens for the Fermilab, which is this red one. And in principle, since these 2 experiments are uncorrelated, you can easily average them, and that would be this purple point here that can be compared then with the standard model I was mentioning before from that theory white paper, and that's where you get this 4.2 sigma. 4.2 sigma means that if you are going to explain this experimental average result with the standard model, the chances to do that is 1 over, I think it was 40,000, 40, so yeah, something like that. So it's pretty difficult, say, no? So here are the numbers that I'm comparing, and that's actually the current situation. The deviation would be 25 units in 10 to the minus 10 with an error order of 6, the combined error order 6. No? So in order to understand this thing, we have to understand a bit better what happened, how they measured, and how you calculate. Okay, I just want to ask you, for those who are say willing to understand better this thing, to keep in mind those numbers. Okay, 25 as a discrepancy, as the numerical discrepancy between theory and experiment, but also the error 6. Okay. Say before entering into the details, I just wanted to just put in the context. So the g-2 experiments have been with muons have been got carried out many times in several places, starting from CERN and then at Brookhaven and now at Fermilab. And these the Fermilab number came from a positive muons. Okay, so you would expect that they will also do it for negative muons at some point, and then you would average, assuming CPT, and then you would really have a reduction of this uncertainty. Beyond that, okay, beyond all these experiments using a storage ring, muon storage ring, there's going to be a completely different setup experiment at the J-Park facility in Japan. They are going to use a penning trap technique, and they are also expecting to have a similar precision as the Fermilab final life of the experiment. I'm not going to comment about this J-Park experiment, but I do have slides in the backup if someone is interested. Okay, so we can discuss it at any moment if you are interested in understanding a bit more how it's going to be this J-Park experiment. Okay, in the J-Park they are going also to measure the hyperfine splitting of the muonium with the same facility. So we are all get advantage of that facility, not only for the g-2 but also for the other constants, the ratio of the mass and electron and muon masses and all these things. So before entering into the detail, just wanted to say that the discrepancy is 25, okay, that here is in units in 10 to the minus 11, so it's 250, is a sort of very large discrepancy. Why I say that? Because if you are going to say the standard model is not the last theory, and you have to complement it with something else, this new physics in a naive picture must have a very low scale, as I showed in this plot, which is pretty old, but just to illustrate. So it's very appealing for model builders to discuss about the g-2, because it requires a not naive or not simple model to accommodate the discrepancy. Because the naive expectation would be very low scale, which is already ruled out by direct searches. Okay, so how do you measure this thing? Well, you do have an storage ring for muons, okay, with a very strong magnetic field, 1.5 Tesla. That's a small object, 15 meters diameter. That is a 7, I think, meters of radius, more or less 7 point something. So at least it's not exactly 15. Where you have a beam of muons, highly polarized, coming from a pion decay at a very particular energy, 3 GeV, 3.1 GeV. They are then very boosted, and they live long within your say storage ring. So you have to kick in them, and then with some say electrodipoles, you will collimate the beam, and then you will observe what happens there. Okay. Then you are going to measure this factor A, the anomalous magnetic moment. How are you going to do that? Well, there are two things that happens here. as soon as you have your muons entering into the storage ring, you are going to observe how they precess around the storage ring. That's the standard cyclotron precision, and that's going to be defined by the magnetic field, the electrical charge, the mass, and the gamma factor, the relativistic gamma factor. Okay, so you can just calculate that. Turns out that this is 100 nanoseconds, something like that, with these energies. So okay, you can measure that. But then on top, because of having spin, the spin and the would interact with the magnetic field, and then the spin would start by just momentum, angular momentum conservation. The spin is going to start processing around the momentum line. Okay, and if you are in a relativistic theory, no quantum effects, say well, beyond the spin, you will say that the precession of the spin around the magnetic moment would coincide with the cyclotron precision. But if you see a departure from that, that would be a sign of that quantum effect. Okay, so you are going to compare both frequencies, the cyclotron one and the spin precision or the Larmor precision one. Then the difference, as you can see here downstairs, is actually a proportional to this factor A that you want to measure. So what you are going to do here is you are going to measure this frequency omega A, you are going to measure the magnetic field, and from those, knowing the electrical charge and the mass of the muon from other experiments, say, you would get the factor A, okay? So just by comparing these two frequencies. But why do you need these muons so at that particular energy, 3.1 GeV? Well, one thing obvious is that you really want to have them traveling around the longest possible. So you want really to have the muons long lived, so you have to boost them in order to observe what happens there. But on top, there's a second reason, as that goes, because of the electric quadrupoles you are going to use to collimate your muon beam. When you look at the equations of motion for that object in presence of a magnetic and electric field, you see that actually the omega A, this difference of frequencies, would know about the electric field here. But you don't want to measure this thing. You really want to measure only the factor proportional to the magnetic field. So you really want that piece of here to be, say, cancel out, to be zero. So since that depends on the object you want to measure and the relativistic gamma factor here, you can easily calculate what would be the energy or the velocity for those muons, so in such a way that this is zero. So you do calculate that, and that's the magic energy. It turns out to be this 3.1 GeV. That's what you need in order to cancel the effect of the quadrupoles into your measurement. Okay, you can say, hey, but how can you know say what velocity if you are using the object you want to measure, so which you in principle do not know, to get the energy, right? How can it seems that so you are just cheating yourself? But it turns out that you already knew in advance how much would be basically a mu, so you can just calculate this thing and then iteratively solve this system of equations. Okay, and of course, if there's a leftover, you're not really matching exactly this equation, you would see a small departure from the plane of movement in the beam. So that can be corrected with the Monte Carlo, and then would induce a systematic error. But those things are well under control because are well known. Okay. So that was the Brookhaven experiment. It turns out that the Fermilab, they use exactly the same framework setup, and actually they even use the same storage ring that's super expensive. And when Brookhaven decided not to run anymore, they move it to Fermilab, which was a very interesting trip via boat going up to the river. There's here a link where you can say, if you are interested to see, that's in Louise, I believe. You can see the magnet here downstairs. There's the Fermilab infrastructure. They had to move the last kilometer were with a truck. So if you are interested, you can see the gallery there with some images. So they go there at Fermilab and they say start running it. And what they are doing, actually, in order to really measure these frequencies, you're going to see how the muon decays within your setup, okay? So the muon would be a weak process decay into an electron, and this is, muons are highly polarized, electrons are highly polarized as well, so you can measure when and where the electron decay happens, and then because you catch up this electron in your calorimeter, that's the sort of signal you have, and then just counting, you would get an image on how this the spin pointing towards with respect of the muon line, okay? And this in the right hand side is the sort of plot you would see, where you see here it seems a solid line, but it is not a solid line. It's just the experiment is so precise that it seems a solid line, and you can see this decreasing, and that's a standard decay rate. Driven by the lifetime of the muon. So you are going to do in order to get the frequency, you're going to fit this data with this equation here, the standard equation coming from the initial bunch of muons, which I believe is around several thousand, 5,000 muons per field. You're going to fit that, and you would get the omega A, okay, from that. Well, actually, the thing is a bit more subtle, because I said before, in order to get omega A, so in order to get A, you want to have omega A, but you also need to know very precisely the magnetic field. So in order to measure the magnetic field at the precision you require, 10 to the minus 10, what you do is actually not really looking at a omega A, but the ratio of two different frequencies, omega A that you are measuring there, with respect of the free proton precision frequency that you measure with exactly the same magnetic field. So in order to, when you do the ratio, you cancel out all the possible uncertainties on the magnetic field. So you don't really rely on the measuring the magnetic field. So the different results from Brookhaven and Fermilab actually come from this ratio, the ratio of these two frequencies here, which that's the number from Fermilab, and that's the other one from the Brookhaven. So I'm sorry. So you measure the thing, and then you get the number you like. The current situation is the following. So they already had at Fermilab 2 runs, I believe, if I understood correctly, but only the first one has been, say, analyzed, and the number we are getting from them is actually the result of only run 1, which is around 5% of the total statistics conceived for the life of this experiment. So that means, since they already had measured run 2, then as soon as they release or they evaluate or the run 2 data, we are going to have at least double statistics. So in a framework of couple of years, so that is soon, say, we are going to have and if nothing else changes, we are going to have a result, a discrepancy, which is very close to be of 5 sigma. Those are just my number, just playing with these ideas, okay? So soon, I say soon because it's only a 2 years framework, we are going to see incredible things here, if everything stays the same, okay? So you see, from the Brookhaven final result 2006 to today, it happened. So there was 15 years of time, okay? But we are going to, yeah, we increase from 3 to something to 4 point something, and soon we are going to say decrease or increase the uncertainty with a similar amount, super soon. That is really pressing also the theory community, right? That's the image of the Fermilab experiment. You see that's beautiful picture where you see the storage ring magnet here. And the advantages of the Fermilab with respect to other, the previous Brookhaven one, is that there in the Brookhaven and Fermilab, they got much more muons, 20 times more muons. And also the magnetic field is calibration is 3 times better measured. So that makes a important for this ratio R, that is actually the measurement between these two frequencies, right? On top, they also have less systematic uncertainties coming from an improved precision frequency measurement. Okay, so that's why it give us this very interesting result, basically statistically driven, with an error statistically driven. I don't know if there are questions, comments here.
Yeah, hi. I had
Hi.
actually a few.
Okay, please.
Or let's say two. One was the 4.7 sigma. Was that like combined with Brookhaven, or this expectation? I mean, sorry.
Correct. That's the combination, the average, the weighted average of the both experiments. Say.
Yeah, that's where I'm heading actually.
Okay.
I was not going. Yeah, I was thinking about the projections that you made on the last slides. But anyway, the relevant question that I was having was, are you, which is a bit unfair, are you the combination of the Fermilab and Brookhaven results?
Yeah.
Is a bit tricky, right? Because I mean, it's the same accelerator and the same ring. So do you know about how they dealt with common systematics?
I see. Yeah, thank you for the question. Let me say, before answering that, when I did my projection, I actually took both numbers into account, but just say reducing this Fermilab uncertainty by the amount of having double statistics. That's what I did. No? So it's really combining. And then yes, you're actually using the same magnet. That's true, but all the other things are different, because the facility at Fermilab and Brookhaven work differently, and the muon beams are different, and the people who are actually working there are different, and so on. No? But if there would be a systematic error in, say, common in both, that you have to take into account when you do the average, anyway, that would go into these uncertainties here, which are, say, subdominant. On the results. No? So you see that in both experiments, the largest source of error is purely statistics. So if from that point, say, from these errors, a part of that would be correlated, you would not notice when you do the average, because that average here comes basically by the statistical thing. It can happen that if you dramatically reduce the statistical error, say basically that you are dominated by the systematic, then you may have to worry about this thing that you were pointing out, which I actually agree with. There may be a systematic, even though I have to say that the calibration of the magnetic field was completely different, right? Because you cannot use the same calibration, the same Monte Carlo. You have to build it up from scratch, at Fermilab. But then, say in several runs, you may have to be worried about that. But then at that, if you reach that level, you will see much more, and nothing else changes. The discrepancy will be by far larger than 5 sigma. No?
Yeah, okay. I mean, I was actually drawing a little bit different conclusion than you from these numbers, because I was thinking, okay, the Brookhaven results are, well, the systematics are quite relevant there. Of course, for the Fermilab, it's much less, but in the end, I agree. It's just like the effect can be like only a difference between. In this context here, something like between 4.1 and 4.2 sigma. There cannot be more effect from the correlation.
Yeah, I definitely agree with you. Yes, yeah, completely agree. Yeah, there are many sources of systematics. One of those could be completely correlated. I think it's okay, but as you say, is not at the level of 4, but maybe under the comma. Yeah, I agree with that. Yeah. You said you had a couple of questions. Did you?
No, the other one you answered because I was wondering on the projections,
Okay.
How you made the projections, from whether you took into account just Fermilab or Fermilab plus Brookhaven.
Okay, no, I just reduced this thing by 2, say, or a square root of 2, and then I just average again all the things. That's what I got.
Yeah,
but that's my numbers, just to give you a feeling, right? How the things are going on. I just wanted to say that they are going very fast. That's my concern, my take from that. Yeah. What else? No. Okay, so if there are no more questions right now about that, we can also discuss later. I just wanted to say, okay, we understand the experimental number, that's the situation. Then we have to also understand the theoretical one. No? How is the where is this number coming? This standard model result comes from that paper that I'm showing you here. That is it's from summer last year, where I just put here some colleagues you may know. That's Elena Pérez del Rio, I believe, is the only Spanish person working on the experimental side. She's from Oviedo, but right now is in Italy, I believe. And there are 3 guys here, Santi Peris, Paulo Sanchez Puertas, and myself, working on the theory side. We are from Barcelona, but the 3 of us right now. And that's how the numbers look like, okay? So when you go to this report, you will see a list of contributions, list of numbers that you have to sum up to get the number I was showing you before. Careful here that the units are 10 to the 11. These should be compared with these 4. This should be 4.3 in 10 to the minus 10, okay? And that at that moment, that was the discrepancy, which today is reduced, okay? I'm very pleased to say that I managed to appear in this table. That's this red thing here, reference 18. It was our contribution to that white paper, and so I'm very proud of that. But actually, it was a very interesting sociological work to get the consensus with so many people. The initial goal was to reduce the error to 1.6 or 16 in these units, but we only reached 40, say. So there's still a lot of work to do, okay? So, and how is that thing? How do you calculate this thing, okay? Remember the words of Arkady Weinstein, g-2 is particle physics in a nutshell. And you see here the nutshell, which is, say, the theoretical calculation includes everything, say, QED, electroweak physics, and hadronic physics. The 99% of the result is QED. You see, it's these sort of diagrams where you only have photons and leptons, okay? And actually you can calculate this thing and you got the number with the precision, which is astonishing, okay? That's 10 to the minus 11, okay? It's one order different, and you see 0.1 in the 10 to the minus. So it's super precise, super well understood, okay? And this actually is a result from a complete 5-loop calculation, 5-loop, okay? Which has been carried out with the Japanese collaboration, Kinoshita et al. It's more than 10 years of calculations, including the 4th and the 5th loop. And now there are also right now analytical cross-checks of the 4th loop and also some numericals for the 5th loop. So we are going to have a full, complete cross-check of that result. So, the QED is interesting because it has actually, the QED part has actually a universal contribution common to all leptons, but because of loop processes that may have a masses running, lepton running in the loops, then you will have a second part which is going to be lepton dependent. So that means you cannot directly compare the g-2 of the electron with the g-2 of the muon. There's not such a naive scaling directly because of these log scales here. Okay, well, that's an example of what would be, that's say here and on the left corner, you have the one loop, that in the right corner, you have the second loop topologies, okay? And you can see that there are many with photons, okay, that they are common, they would go to this A1, but then you can see here a vacuum polarization topology where you have an insertion here of say the muon contribution to the vacuum propagation electron or tau. Okay, depending on who is there and what is the external lepton, then the result will change. Okay, that's a two-loop thing. But these guys calculated up to 5 loop, and that's an example of the topologies you have to calculate. I mean, oh yeah, that's wow, incredible. These amounts to say around 12,000 diagrams. So it's an enormous, gigantic work here. Excellent. So at the precision, actually, we are calculating. You are
Sorry,
measuring.
Pere.
Yes.
I have a question.
Okay.
Well, sorry.
Okay, go ahead, please.
Yes. If you take from QED the error for the from loop computation, so the part that has been checked by other group, the error will be compatible with other sources, or will it still be much smaller?
You mean if I go here and you
take the only the for loop, I mean the part that has to be checked.
I don't know the number by heart, but if you okay, but if you would use only the for loop result, not the fifth, but the for loop, yeah, exactly the number would slightly be different, and the error would be slightly larger because you are missing a full fifth loop that you can calculate in a way by just looking at the size of the fourth. But if I remember well, the fourth loop is enough for the experimental precision.
Okay, thank you.
So that's in a way, it is the goal to calculate the fifth loop was only to reduce the error, not to move really the central value. What happened is that you at the fourth loop, you estimate the fifth loop by just a naive counting. I just did naive counting, but as soon as you introduce new loops, there will be new topologies that you didn't have before that you cannot estimate just by counting, say. So that was the goal of the fifth loop result. So everything is very consistent, and then you get a so stream precise result. This is a purely numerical uncertainty coming from the numerical integrals you are performing your Monte Carlo when you reduce all these diagrams to master integrals. Then you run them in a Monte Carlo. Then that's the numerical precision you have. So if they would like, there are techniques to reduce even further this number. Okay, if we would need it at some point, say. I don't think they are going to go ever for a 6 loop. It's too much, I believe. Yeah. Okay, but as I was saying, now the precision we are discussing, electroweak effects are also important. Why is that? If you guys remember, the current discrepancy between theory and experiment, it was 25 in 10 to the minus 10. But you see, the full electroweak sector is already contributed by 15. So you really have to put that into account, include that, because the error, the combined errors, is 6. So that's more than 2 sigma effect there. So that you must include that. And actually, these things are calculated. You can see here the topologies, the examples of topologies at one loop with the W's here, neutrino, or the Z contribution here. This is the standard polarization of the Z boson. And here you see a second loop effect, or one example of the second loop you can see here the Higgs propagating. Okay. Those numbers are very small, and the reason is because as soon as you include the electroweak sector, you have to include you are going to do it in an effective theory, a manner where you can see here the G Fermi, and then you would have to include, you have to pay a price of including them via the lepton mass. That's why these numbers are so small. Okay, and here the details of them, actually the uncertainties on the masses of the W or the Z are not really important here. Okay, but you have to definitely include them. And then the most intriguing part is the one that comes from hadronic effects. Okay, so QED and electroweak are quite well understood, especially via the uncertainties, but the hadronic part is going to trigger the largest error. Okay, and that's the image that we are having. So I didn't say that, so let me go back because I missed it here. Sorry. When I was presenting the 4 contributions, you see that to get the final standard model result, the error is 4 10 to the minus 10. This number comes from this this topology, this diagram here. Okay, so understanding this error here, or these numbers here with this loop, is understanding the standard model uncertainty. That's what I'm going to do right now, and that's the snapshot of the situation. The contribution of this object has been, say, floating around some number in the last years, but recently you can see these two different results agree very well to each other, then given some confidence that we understand this hadronic vacuum polarization. But what is that? What is that? Okay, let me go to the detail. So one of the topologies from QED was this photon propagating, and I showed you the second loop order, you may have leptons here, an electron and a muon running here. But yeah, because of the electrical charge, you can also have quarks here. So you may have a vacuum polarization driven by hadrons here. Why I say hadrons? Because, well, having quarks here in a loop, this photon can have momentum which is very small or momentum which is very large. Okay, at some point, if the momentum is low enough, you will not have purely quarks, but you will have hadrons here. So the perturbative QCD theory cannot be used to calculate this diagram. So what are you going to do? So you want really to calculate this thing, which is an object which is quite, say, is a second order effect, which is suppressed, okay? But you want it to have it in the largest precision possible. So you really want to understand this loop very well, and then you are going to use the optical theorem instead of perturbative QCD. The optical theorem relates this hadronic vacuum polarization with this hadronic cross-section here, where you can, that's inclusive hadronic cross-section that you can actually measure, that you are going to use this data, put it into here in the cross-section, and this integral is going to tell you, this integral is going to give you the contribution you are looking for. Here, K is a kernel, is a purely kinematic function that is well understood. It's just the kinematics of this process here, which is actually peaked at low energies, you see, but also the cross-section is peaked at low energy. So this integral is very peaked at low energies. So even though you should integrate from threshold, say, hadronic threshold, up to infinity, the more relevant part will be at low energies. Okay, and that's the current situation. There are many experimental collaborations using meson factories to explore this energy region, which is actually dominated, even though it's an inclusive measurement, it's actually dominated by the lowest channel possible, which is the one going by 2 pions, and that's an example of the situation with 2 pions. There are many collaborations here. Okay. But as I said, it's an inclusive measurement. So what you have to do is you calculate channel by channel, and you then sum up all the channels to get the inclusive cross section. And this is the example taken by this collaboration, Kizevars et al., where they look at the different experimental measurements for each channel, and they combine it with the proper correlations and so on and so forth, and then they got the numbers. So, and as you can see, yeah, here that's the energy range they cover, and that's the result. As you can see, the largest contribution in all this column here comes from, yes, indeed, the 2 pion contribution here. No, the final number is going to be around 700. The 2 pions is already 500. Okay, so you're going to do a scan. Whenever you have data for the channel, you put it in the channel, but at some point you will not have any more data for that channel, so you're going to use perturbative QCD, but now safely, because you are going to use it in a range where do you believe the theory works. Okay. Of course, the heavy quarks are also included, say, for example, the charm via the g-2, and also, or the upsilons for the bottom quark. Okay. So that explains this red number. This is this number that you got from there, where the uncertainty comes from the uncertainty of the different channels when you combine, and that's the number they would provide in that reference. As soon as you include higher orders effects, no, you can have the vacuum polarization, the hadronic vacuum polarization, plus other insertions from QED in the very same loop, which will be higher order, but you can also include them. That would only modify the kernel, but you know that how to do that. You do that, you sum up, and that's the final number. Okay.
Sorry, Pere, this is Bernardo Deva. I have a small question.
Sure.
We met together, right, virtually at least. I have a small question here. In that perturbative QCD part that you just mentioned, there is some treatment for the isospin breaking between the U and D quarks, or it is more general than that?
Oh, beautiful. I see. No, not at all. Not at all. No, zero. They are actually very good. Actually, you have, say, experimental data up to 11 GeV. I hope you can see the numbers here.
Yes.
And from that point on, you use massless quarks. For the light quarks, up-down strange would be massless. And the charm and the bottom would also be massless, but you would include mass corrections in a perturbative QCD calculation. So in that, say, window, which is actually not really important here, you can see in this chart here, that's the energy. And this is the amount that contributes to the integral. So 95% is from threshold to 2 GeV. And we are now discussing from 11 to infinity, it's maybe a percent level, for which you believe that neglecting their masses is it's okay. You may actually ask for another thing, and that I'm going to comment later. That is going to be what would happen if instead of using pi plus pi minus, you would use measurements from tau decays that would have pi plus pi zero data, pi naught. Then you would really have to include isospin breaking effects to correlate with this one. But I'm going to comment on that in a couple of slides.
Okay, thanks.
Thanks for the question. Yeah, okay, so that was the number from that collaboration, and you see, well, okay, the other collaboration, which is using same data, has basically the same number, okay, 2.4, then you would naively average these things, but then you go to the white paper and you observe that, hey, what happened here? The error is much larger when you combine both instead of much smaller. How that happened here? Is that the point here, and that's why I'm a bit, say, joking around, is that when you look at carefully how they did this sum, analyzing channel by channel, you see discrepancies there. Even though the final number, the final central value is so close, it is actually hiding that the different analyses are really different. You can see, for example, the pi plus pi minus channel, which is the largest one, looking at one work or another, the difference between the central values which is here in the last column, is by far larger than the individual uncertainties attributed to that channel. Yeah, so that poses a problem. How you do combine these things? So the strategy followed by the white paper, say, theory community, was to enlarge the uncertainty by half of the distance of the central value, okay? Which is basically, at the end of the day, is basically, numerically, is basically taking this 3.4 instead of 2.5, 2.6 for the error. But then still, you would combine the errors in quadrature for the different channels, assuming that these discrepancies here, which are larger actually for are large for those channels contributing the most, they are combining quadrature. But they are systematic differences, right? So if I would be critical, I would suggest to combine these systematic uncertainties linearly, not in quadrature. So if you do that for all the channels and you combine these differences as a systematic errors linearly, not in quadrature, your error, instead of being 4.2, 4.0 would be 6.5. So much larger error. That's actually, that's a disclaimer, that's my number, okay? That's the one from the white paper, and that's my own number just for you for discussing, trigger discussion here. So just to play around, no? And actually, the thing can be even more, you can even criticize the results even more. Why is that? Because for getting this pi plus pi minus result, which is the one that contributes the most, there are many collaborations producing results Clio, the Russia S&D, Best 3 from China, CMD, Babar, Chloe. Okay, and you see the results for a particular window. Okay, a window of 300 MeV. Okay, in that very particular window that you can easily integrate the data. Okay, you see the scatter of the results. Chloe and Babar do not agree with each other. So when you do the combination to get the final contribution, you have to do something. The standard thing would be to enlarge the errors by half of the distance and then do the average. But then what happens there is that depending on you do the correlations and so on and so forth, you would get the different numbers. So these different numbers, this difference 3.4 comes from the way you do this combination. Let me insist, this 3.4 is, remember the full standard model error is 4. And we are seeing already 3.4 in this particular channel. This is a small subtlety driven the full error almost, okay? So that must be understood very carefully. So my particular proposal would be to be super conservative in that respect and say, okay, let me add not quadratically, but linearly, the difference between these two collaborations as a purely systematic error. So I was already conservative before, saying when I do the full channel combination 6.5, but now I would add the difference. The difference, as you can see from the numbers, is 10. So I would add 5 as a purely conservative systematic error. Okay. So when you do that, then the error would be much, much larger from this vacuum polarization prediction using standard model. Okay. There's another discussion coming from why don't you use tau data, which is super precise, or much more precise than the plus minus. No, you can see the difference here. Tau data is much more precise with respect of the scatter of this thing. What happens is that if you want to use tau data is not going to produce pi plus pi minus, but pi plus pi naught, and then you have to use isospin breaking effects. But if you do that those things are basically well understood, and then you can actually use a formula to say unfold this effect. For example, this Miranda Roche 2020 paper, they got this number 700 with an error which is 6, which is of the order slightly larger than the e plus e minus 1 provided in the white paper. But you see the central value is much larger, okay? And if you go to this final result I was showing you before with my critical reading, and then you compare with also lattice simulations, you see what is the situation here. No? So we have in red the data using e plus e minus, okay? In blue, we use, you see here, lattice simulations from lattice QCD simulations, okay? When these blue points reaches this green area, they would say that there's no new physics because the contribution they are getting for this vacuum polarization is that large that the discrepancy between theory and experiment for the G-2 disappears, okay? The blue column is the average of those. What happened recently is that it was exactly the same day that the Fermilab released their number, the BMW collaboration, lattice collaboration, published in Nature a new first time per mil level precision to percent level precision for this vacuum polarization, and that's the number. As you see, it touches at 1 sigma with the no-new physics region. And what is I also find very much appealing is that it also touches nicely with this brown point, which is the result coming from tau decays. So I believe that this is the situation we have to understand. Before claiming new physics, which is definitely very appealing, we have to understand this situation. How do you compare the plus and minus? Also, this systematic error I was discussing, and with this lattice and tau decays. If I take the difference between the lattice result and the phenomenological evaluations here, the difference is 13 in 10 to the minus 10. But I was also saying before that if you would be super conservative, you would have an error of 11. Then the things would be much more compatible, sorry. So it would have a nicer picture in agreement, right? And and then would make the situation a bit more, say, complete, in my opinion. Okay. But that's not the final story. There's still a higher order effect, which is called the hadronic light by light. I'm going to run it fast because I'm out of time already. And the hadronic light by light is a multi-scale problem. You have a two-loop effect with quarks running here. You don't know how to treat that. The standard thing, right now, I'm going very fast, is to use experimental data to build up these blobs here that are the individual contributions to that diagram whenever you have pseudoscalar or scalar particles running. So that's a mathematical mechanism to split this diagram into pieces you can actually measure, and then you use experimental data for those, and then you calculate. And those are the results. So in the white paper, we have the results. For the largest one comes from a pi knot. Here it changed. And then you will have the other pseudoscalars, eta and eta prime, and then with subleading effects coming from other contributions here. And I can say that this error here, which is actually one of the largest, is going to be reduced as soon as we understand a bit better these axial contributions, okay? But I don't want to stand more on that. This is a subleading effect, which you can also criticize in the way you are summing up the errors. You can also perform a critical reading and say, I don't like the way to combine the errors in quadrature. I would prefer to, whenever they are systematic errors, do it in linearly, and then that would be the final result, okay? And then you would combine. That was the final result shown by the Fermilab, and if you use my numbers, that's just my play, you would have a much larger standard model error that would tell you that actually the discrepancy is at the level of 2 sigma, okay? That would be only for the error, but not the central value. You see, the central value is still quite large. 25 is much, much larger than the full electroweak contribution, okay? So that's there's a thing to understand here. I am emphasizing this thing because if I go to new physics, I'm going to finish the discussion. If I go to a naive new physics, for example, taking a generic Z prime a model contribution, okay? I'm using a code provided by Queiroz and Schaeffer in this paper. They were very kind to provide their codes. And here you see the plot, the scale of the new particle, okay, here. And in green, you would see two different lines. Solid line is the actual discrepancy with the Fermilab and the white paper, okay? If you would use my, say, numbers, if you like, that would be this dashed line, okay? But it makes no, especially, doesn't make much difference here. What is interesting is that if you are going to explain the discrepancy with the Z prime boson, with the standard coupling, the vector and the axial coupling equal to 1, that's the solid line. So you would need a very low, a very, say, sort of light Z prime boson. And this is already excluded by Leb many years ago, okay? So if you want to explain, if you want to use a Z prime, you would like to have a smaller discrepancy with respect to theory and experiment, okay? These 25 units to be rather 10. That would be this line here, which would induce a larger scale if you are allowing yourself to change slightly the couplings, okay? Z prime might not be the best candidate. That was just an example. That's this loop, which is sort of easy to calculate. That's a result. Currently, the most appealing is a vector leptoquark, which actually has connections to another flavor anomaly observed by, for example, you guys in the LHCb, RK, for example. That's a good candidate because it's quite elusive. And what is the idea here? You would have a similar situation for standard couplings. You would require leptoquark to be, say, not that massive, but as soon as you allow yourself to change the coupling, for example, in this combination here, purely vectorial, then you would be fine having a mass of 1.5 TeV, something like that. And if the discrepancy would be smaller, or the 10, so these 10 units, then you would go to, say, 2 TeV with a regular coupling like this. No? And that's very interesting because that would also match, if that would be the explanation, it would also match with the RK observed by the HCV. So that's the scale, the typical scale. So if we are going to believe the other anomalies, you would rather like to have small discrepancy here in the g-2 as well. Okay.
Sorry, and the fact that there might be in that anomaly a difference between the muon and the electron that would have a contribution for this lepton quark that is non-universal, would have any specific implication here?
Oh, yeah, well, that's another advantage of these lepton quarks. You can select here, these are these red points here. I just wanted also to say that in these couplings, you can select wherever you like. You can define that your lepton quark only touches one generation of quarks or leptons, for example, giving a particular flavor structure, avoiding spoiling, say, electron physics, if that's the concern. You can also define different couplings. You can also touch everything, but the different hierarchies here, that's a flexibility that you have, sorry, with these models of lepton quarks. So in principle, you may have, in that scales, you may have an explanation for the g-2 of the muon without spoiling the g-2 of the electron that I have in the next slide, I believe.
Okay.
Yeah, so that's a way. That's why it's so attractive, this lepton quark, because it's quite elusive. There are many ways, say, to navigate across all these anomalies or other objects which have no anomaly. No? And actually, that's maybe what you were referring, is that we have been discussing about the g-2 of the muon, but it turns out that the g-2 of the electron is also very interesting, because it's also related with the measurement of the electromagnetic coupling constant. That these are things that you measure with a different setup. You use a mass spectrometer, you take your a particular hot atom, and then you say send a photon with a particular energy to that, and you measure the recoil of that atom. You can use a cesium in the left-hand side that was published in Science 2018. It's a Princeton collaboration, I believe. Or you can use rubidium, and that was published in Nature 2020. And via measuring the recoil of that atom, you can measure the electromagnetic coupling constant using this formula here upstairs. And with that alpha electromagnetic, you go to the formula of the 5-loop QED result for the g-2 of the electron, and then you predict. You measure the g-2 of the electron in a penning trap machine, and then you compare. If you use the alpha electromagnetic from the cesium, you see a discrepancy between theory and experiment for the g-2 of the electron of minus 10 to the 4 sigma, while if you use the rubidium, you find basically an agreement. Okay. So as we were just discussing, if you are going to include new physics for the muon, you have to be careful what do you do with the electron, no? In order to try to understand this picture here. Just wanted to say that if you compare the cesium and the rubidium results, the distance is larger than 5 sigma. So something is going on here, I would say. And this is for future work, I believe. Okay. So that's all these fairy tale I wanted to tell you. But as I promised, there are no conclusions. I would like to say that this is still open. There are many issues here, but times are pressing. I mean, Fermilab is going to release new things in a couple of years. So we have to really work hard. And I was wondering whether in this situation where E plus E minus to pi plus pi minus is an issue, whether the LXCV collaboration could provide some new insights, as Babar did a few years ago. You guys are very good in K-pi channels. Why not pi-pi? But that's a discussion. Okay.
Okay. Thank you very much.
Took a bit longer than expected. Sorry.
Do we have any question from the room? Or let me check if somebody raised their hand or.
So I have a question. So all the when you put the diagram in which you calculate the hadronic vacuum polarization, you only took into account the last two measurements. Why is that? So why did you adjust those two more than the others? Are you sure they are definitely better than the previous ones?
Yes, well, they are basically from the same collaborations. I say collaboration, but it's actually theoreticians, theoretician collaboration, say. And they actually,
Yeah,
they are the same people, but including more data. Why is that? What happened here in between? So there you see, for example, this red should correspond to this blue, but an update, and K and T should also appear here.
and these values include lattice calculations, or
no, not at all, not at all. No, no lattice. What they did include is the last best 3 result. Best 3 provided new data for the Z plus Z minus channel, pi plus pi minus channel, sorry. So the only collaborations including this new set of data are those here. That's why you use them for the average.
And what evidence do we have that this effective theory, so to say, of understanding this as the pions is enough to describe the process? Because it doesn't agree with the lattice calculation, right?
Yeah, in that plot, right? Are you referring to this discrepancy here, or this distance, right, in between this cyan and the red, right?
Yeah.
And the question was, I couldn't hear you well. Sorry for.
As far as I understood, so those guys are assuming that to calculate that number you don't need lattice, but it's enough to know some experimental values for pion decays and so on. And so I'm asking, why is that reasonable compared to just using lattice?
Okay, well, wow, that's a difficult question. Well, I believe, so what you have to really calculate, let me go back, would be, that's the integral you like to calculate. That's what you need, sorry. That is an integral, they have to cover all this energy, okay? From threshold to infinity for a hadronic cross-section, which is inclusive, all data there, all the hadrons there, no? So since you cannot calculate the inclusive cross-section at low energies, but you do at large energies, but not at low, what you are going to do is for the low energy part, you are going to sum all the channels. So in principle, you are doing what you have to do. So you sum up everything. That seems reasonable. It turns out, just by the scales of the problem, that the pions are the dominant one, okay? And actually, that's peaked at low energies. That's why, actually, at the beginning, you would not be so confident with the lattice results, because that's in principle, okay? When you do the simulation within a lattice, see lattice spacing and continuum extrapolations for that particular small energy region, low energy region, was difficult. That's why the errors were large here, no? As you can see.
Yeah.
Compared, no? The surprise what came with this one, no? The BMW got this super precise number, telling you that all these systematic errors from the lattice is much better under control. Then the question is, can you?
In the other approach, you're taking sort of an effective field theory description, which I don't know. I mean, I'm not saying it's not justified. I just want to know if it's justified. Just to think about it only as just getting that number from pion decays and so on.
Yeah, but in what respect do you say that is an effective approach? You are just summing the.
Yes, I have a question that is maybe related.
Okay.
I mean, when you show this diagram, this process is virtual. I mean, the triangle. No, the diagram you have on the left,
What?
I mean, this is a virtual diagram, right? There is no cut here. Well, when you're using the optical theorem, you are using a cut, right? You're putting a cut there. So there must be a way, something that you are using to relate the two quantities. There is some theory involved, right?
Correct, the optical theorem.
And then okay, but the optical theorem will give you only the imaginary part of this diagram. You also need the real part, right? And my question would be, what do they actually measure in the lattice? So is this operator, or do they use also the optical theorem?
Okay. Okay, in the lattice, they actually do the simulation in the Euclidean space, not in the time-like. No, that's in the on the other side of the correlator. So they actually use the same correlator, pi, the vector correlator, but in the Euclidean. So for minus s, if you like. And there, the problems are completely different there. No? That's the same object. You can actually relate the integral you really want, as you say. No, that's related to the imaginary part of the correlator. That's what you really need. This is the production part. But you can also calculate the other side and then go back to what you need via just a kinematic function. That's what they do in the lattice. Yeah, and respect of the threshold thing that you were really, I agree. So if you are only looking at quarks, you would have to start in a different threshold. The threshold will be the quark masses up to infinity, but you do relate with the optical theorem the different thresholds, no? Also, in order to avoid divergences, standard divergences you would have dealing with massless quarks, if you like. No? So in that respect, I would say the framework is well understood, and I don't really see it as an effective thing because of what I was saying before. No, you would take all the channels, and for each channel you would sum up from, say, threshold up to infinity, and then you will sum the different contributions on top. No? Everything you can measure. Of course, there are missing channels here. You can have E plus, E minus 2, I don't know, 20 pions, if you like. That must be included. But that's, you can also relate it via counting of the couplings that should be very, very small. So you also you must include in your uncertainty an estimate of the missing states. But as far as I understand, those things are very, very small.
Okay, thank you.
I hope I managed to answer in a way. What else? Do you have more questions, comments here?
Yes. Yes, I don't see more. So, okay. If not, then we can thank the Pere again.
It was my pleasure. I mean, you have my email on the slide, right? So